Right, boys and girls, let's get going. In the previous two lectures, I taught you in a boring and technical way how you solve differential equations. Today we will look at how you make them. That is, at ways of starting with the real physical, chemical, biological systems and producing a model for them. And it's considerably more interesting and light-hearted than actually solving these models afterwards. And you can take heart at the fact that actually these days we usually subcontract the solving of the equations to a powerful enough computer. But the task of designing a model is still human creativity, and this is what we will be dealing with today. Now, we were thinking when we were formulating this lecture that, okay, we could have taken examples from chemical engineering, but they would again be boring and technical. Considerably more interesting and easy to understand area is actually biology. You have already seen ecological models a few lectures ago. We will now look at population dynamics models and actually retrace history. So start in the 13th century and get to about 1930s, I think, today in terms of how understanding of the dynamics and its mathematical description and biological models have evolved. Now the story, at least in Europe, at least the earliest I could find in the literature, began in 1205 with Fibonacci, an Italian Catholic priest who was sitting and thinking, well, why don't I make a model of how living things reproduce? And the result was Fibonacci numbers, which you must have come across, but today will be the explanation of what they actually meant. So item 1, Fibonacci. So round about 1200. His numbers are quite easy. Xk plus 1 is xk plus xk minus 1. So a recursively defined sequence where the next number in the sequence is the sum of the previous two. Now, there's a practical example of that in the university canteen. They serve what I call the Fibonacci salad, which is the mixture of yesterday's salad and the salad from the day before. So taste. But the way Fibonacci introduced that is by looking at how rabbits procreate. Now, as you'll see in a moment, as a Catholic priest, he had a pretty approximate idea of how things reproduce. And so he makes the following assumptions. He said rabbits occur in pairs. And then B takes a pair and months to grow up, and also a month to produce another pair. And then, so this is C, and then D, rabbits are immortal. Another interesting assumption to make. And then, well, let's take a look. So we start with one pair of rabbits. Okay, so month number 0, starting point, a pair of young rabbits. Month number 2, the pair has grown up. Month number 3, the pair has produced another pair. We now have 2 pairs of rabbits. Month number 4, the 2 pairs of rabbits have produced another pair of rabbits, or rather, the one that was old produced the next pair, and the one that was young grew up. So we have now 3 pairs of rabbits. Now, those that were young have grown up, those that were grown up have produced their own pairs. We have 5 pairs of rabbits, and so on. So these are Fibonacci's numbers, and of course they occur whenever similar phenomena take place anywhere in physical sciences, and there are plenty of such situations. And so in quite a few places in chemistry, physics, engineering, and actually pure mathematics as well, you will see numbers of this type. But this is the earliest, at least here in Europe, a vaguely sensible model of population. Now, as you can see, it is discrete. That is, there's no way to turn this into a differential equation because, well, rabbit count is not a differentiable function. It makes discontinuous chunks, and we are moving in discrete time increments. So these are difference equations, but these are not differential equations. Okay, fast forward to Britain, and the year is 1798. Malthus. So around about 1800. Another Catholic priest with another set of very approximate ideas about what he was writing. He said, okay, let X be the population count in Britain, and let us think about what's going to happen if we look at an increment in time. So t plus delta, step forward in time. Well, clearly the population count at t plus delta t will be the population count at t plus some modifications. He said, well, okay, the more people there are, the more are going to get born in that period. So he said, okay, let the birth rate be A, and then current population count, and the longer you give the population, the more it will reproduce. So A, x of t delta. And then, of course, there will be death. So the death rate, B. And then again, the more people there are, the more will die per unit time. So x of t delta t. And you can see how this connects to chemical kinetics. We were looking at chemical reactions. Well, the more substance there is, the more reacts per unit time. So this is instantly transferable to your chemicals. Okay, Malthus said, let's do a bit of mathematics with this. By 1800, calculus was exceptionally well understood. Right? You know, Laplace, Lagrange, Newton and Leibniz have all been long dead, and their books became famous. So differential calculus was pretty well understood, particularly by the monks who had the time to study it. So here, remember the definition of a derivative, right? F prime of x was f, or rather, shall we use t in here? T was f of t plus delta t minus f of t over delta t, and the limit delta t to 0. Well, Malthus saw that actually he has all the components in here for a derivative, right? Here's our function of t plus delta t. The original function is something that refers to delta t. So why don't we move this x over to the left-hand side and divide both sides by delta t? So x of t plus delta t minus x of t over delta t is a, and since this is this should actually be minus, a minus b x of t. Well, nice. Why don't we make the interval small? So if we take the limit of delta t to 0, it's dx by dt is a minus b x of t. And this is the equation that Malthus derived. He called this difference alpha. So the actual equation is d by dt x of t is alpha x of t. To you, this is first order chemical kinetics. To Malthus, this is population dynamics. Now, this difference between the birth rate and the death rate is quite critical because it determines whether alpha is a positive or a negative number. Now, Malthus solved this and plotted the equation, and let's do likewise and let us discuss what we are going to see. As you well know, the solution for this is x of t is x of 0 e alpha t. Let's look at our x x of 0 here, and this will be time, and this will be x of t. In the case where the Malthus coefficient is positive, we will have an exponential that just grows. So that goes up. And this is for alpha greater than 0. In situations where alpha is negative, we have the standard exponential decay. Approaches 0. So this is alpha less than 0. And if alpha is exactly 0, then the derivative is 0, the population doesn't change, but that's presumably an unstable situation because it's hard to have the birth rate exactly matching up with the death rate. This is alpha 0. When he published this, 1798, there was, well, it didn't help that he was pretty alarmist about that, reminiscent actually of a certain girl on the television. He said, well, look, from the census at the time, he could conclude that actually the Malthusian coefficient is positive, that is, the birth rate actually greatly exceeded the death rate in Britain at the time. But of course, what this means is exponential population growth. And then he looked at the census data and saw the following. If this is the actual population of the world, and the data was actually available, at least for Europe and the parts of the world where a British Empire could reasonably reach, if that was 1700 and that was 1800 and 1900, actually, way after Malthus himself died, the dynamics looked pretty exponential. And of course, later we know that this has slowed down, but in Malthus' times, this wasn't known. We are looking at that sort of curve, and the knowledge that people at the time had was up to here. Perfect exponential. I've got it in your handout from the Office of National Statistics, I think. Obviously unsustainable. The conclusion that a lot of people have made is that we are all going to die because at some point the population will run out of resources. And from the history of his own continent up to 1800, Malthus could quite reliably conclude that the way the population is kept at bay is by several very pleasant things like epidemics, wars, and famines. He said, well, okay, the population is going to grow up, and then there will be an epidemic, the war, and a famine, and the population will crash back down again. Now, well, so essentially a fairly simple mathematical model predicted disastrous scenarios. I mean, nothing's really changed since those days, you might agree. Okay, so this is the fairly simple one based on Malthus's assumptions about how people are born and how they are dying. The more general case of such models would, of course, not have strict proportionality, right? The birth rate is not a function, a linear function of population count, but it's quite certain that it is some function of the population count. So why don't we now generalize this into the more general Malthus type population models? So item 3, Malthus type models. We will say, okay, these are not actually linear functions with just the coefficient a, but these are some functions nonetheless. We will say x of t plus delta t will be x of t plus some function b, and it will stand for birth, and that's the function of the current population count and time. And then there will be a function d for death, and that is the function of the current population count and time. More specifically, we will assume that both are invariant with respect to history, and so they are not functions of absolute time, they are only function of this time increment. So we will put deltas. So it's a function of x and a function of delta. Okay, now, but we want delta t to be relatively small because we are fishing for the differential equation in the end. So why don't we do the following? We will say v of x delta t. We will just make a Taylor series out of it. I will remind you what Taylor series is. For a function of some small parameter alpha, this is some of 0 to infinity, f hence derivative of 0 over n factorial over to the. So in our case, the small parameter is t, and we will take this series only to the second term. So we will say that this is b of x 0 plus the derivative dB by d time, which we will call b of t times delta t. There are further terms, but they will actually vanish in due course when we take that limit. And the same for this. So d delta t is d of x 0 plus d of time. Am I actually using d? Okay, well, slight collision t delta t. Okay, so far so good. Let us now philosophize a little bit about these birth rates and death rates. If we look at the birth rate in the population that has 0 population count, well, if there's a 0 population count, nobody's there to reproduce. 0. The same applies to death rate. If there is no population, nothing dies. Also, if we have some population here, but we didn't give it any time, then it wouldn't have time to reproduce. So the birth count at a 0 time increment must likewise be 0. It's the same for death count. It has the time to die, nobody died. 0. So there's quite a lot of additional information. Most notably, our b of x 0 is going to be 0 and d of x 0 is going to be 0, and so we can simplify the expressions. Okay, let's plug all of that in and do the simplifications. Then we have x of t plus delta t. We will have x of t plus this b of x that we have there. Actually, it shouldn't be t, should be x in here. Because time is set to just fixed. Okay, so b of x delta t, and then plus, and probably another thing is in order. Let's explicitly say that, okay, d of x will be a positive number, and since they're dying, there's a minus in here. To make things a bit more intuitive, so we will have minus than d of x delta t. Okay, now we do exactly the same as Malthus did, yet again we move x over there, divide both sides by delta t. We will have x of t plus delta t minus x of t over delta t is our b of x minus t of x, and that's the limit. So when we take it, we've got dx by t, that's the limit, is b of x minus t of x, where those two things are the birth rate function and death rate function. So we are no longer constrained by the requirement to have anything specific in here, but we have derived a more general equation that our population dynamics must have. And then, of course, what instantly then becomes pertinent is the ability to study the entire class of such equations. Under what conditions do populations die out? Under what conditions do they proliferate uncontrollably? What leads to our, well, apparently reasonably happy existence here on Earth, where the population increases seem to be tapering out without any major disasters, at least, you know, in the last 50 to 70 years. So let's take a look at the general methods of how one analyzes the behavior here. So the only thing we know about this equation is that it's first order in time. Actually, a lot of physics is first order in time. And then we know nothing about B and D because they're dependent on the country, they're dependent on the weather, they're dependent on just about anything. How do we analyze such situations? And that's the next item on our agenda. It's called phase diagrams. Four phase diagrams. Imagine we were to plot and the following slightly counterintuitive thing. Look here. This is what's called an autonomous differential equation. I've introduced them because these are functions of x, but there's no free term. There are no external influences. This system evolves autonomously. What we will plot here is x. So that is the population. And then on the y-axis, we will plot this derivative. So dx by dt. Because ultimately this is what the differential equation is about, right? If you say, okay, assuming my population is x, what is the rate of my population growth or decay? And we don't really know what this function is going to be, but it will probably be wiggly and wobbly, hypothetically, like that. Let's take a look at what that means practically. If I am sitting somewhere here, so my population is tiny. This hypothetical function that we have says, okay, if you are sitting here, then your rate, your derivative is positive, so the population is going to grow. But the population is our x. And so what this says, if you are here, you will be moving in this direction. If we are sitting there, well, that's our population, but the population growth rate is negative. The population will be reduced. Population is x, we will be moving in that direction. Here again, the population is positive. Well, presumably there has been a critical mass and they've now got enough scientists, so they invented medicine. They stopped dying out at quite the same rate. And so actually at this population count, the growth is still positive, which means we will be moving in this direction. And then they invented some super weapons and started a bunch of wars. And so populations with this population head count will be moving. Notice there are two classes of points here. There are points into which the arrows are moving, like here and here. And there are points out of which the arrows are moving, like this point there. They are called stable and unstable stationary points. Now, at this point, the blue line crosses 0, so the population growth is 0. So when the population starts here, it will eventually arrive here and then stop changing, because the derivative is now 0. If it begins here, it will arrive back there and again stop changing. When you perturb the system out of this point, the system goes back. This is called a stable stationary point. If you look at the little rectangle, however, okay, if we are sitting precisely in this point, like a ball balanced precisely precisely on the top of some hill, or a pencil balanced precisely on its tip, well, it'll stand there. But the tiniest perturbation, the moment we move a little bit away, we are hitting this arrow or that arrow, we will move out and actually drop into the nearest stable point. So even though, technically speaking, if you start precisely here, you remain there, it is an unstable situation. So this is the name. Unstable station. And we are quite interested in finding out, in particular, what are stable and unstable stationary points of our population dynamics. Or you as chemists would be really interested in finding what are the stable stationary points of your chemical reactor. If that corresponds to nothing being there, or if that stationary point is located at a situation that has the pressure that your structure is unable to sustain, then you have a problem. So this is how those things are studied. You have a first order differential equation, you plot the rate against the current state variable, and you look at where the things go. Okay, so as an example of that, let us consider an extension of Malthus's model that actually put an end to the scaremongering that went on for quite some years. This was proposed in 1838 by Verhulst, a Frenchman, who did the following. He said, well, it's not actually just the linear terms that you have in Malthus's equation. So let's draw Malthus one, x by dt is alpha x, and specifically assume that alpha is positive. So we have a Malthusian disaster in the making. What Verhulst said is, well, it's not just each individual in isolation, right? These individuals meet. As chemists, you know that the corresponding probabilities are proportional to the square of the concentration, so we would have the square as population count. But these meetings in particular are a source of mortality, because mortality proceeds from epidemics, it proceeds from wars, it proceeds from individuals simply fighting, if you've ever been in a zoo. So we must have, therefore, a negative quadratic term in here, beta x squared, corresponding to two individuals meeting and just hating each other so much that they become a source of mortality for each other. So, physically speaking, we have a balancing term. So Malthus's model was unstable because for positive alphas as just a runaway. Let us look at the phase diagram of this model and try and analyze its dynamics. So if this is our dt, and this is x, and alpha is positive and beta is negative, let us think about what this is. When x is 0, the right-hand side is 0, so we begin here. And then there is another 0 at alpha over beta, which just solves the quadratic equation. And it's an inverted parabola, so it does this. Okay, let's take a look at the stability of the corresponding points. If we start here, the population growth rate is positive, so actually this goes there. If we start here, the population growth rate is negative, so the arrow moves here. And so this is an unstable stationary point. When there is nothing in your population, of course nothing will appear, but the moment a pair of tiny little rabbits just squeaks into your ecological niche, they start proliferating. And so you go there. And then, well, there's so many rabbits that they start fighting over resources, and this is a stable stationary point because the arrows converge into it. If there are too few rabbits for the resources available, they will proliferate and actually consume them. If there are too many rabbits for the resources available, well, they'll die of hunger, and so you're getting in here. And so actually in the Verhulst model there is a stable stationary point. And this in population dynamics became known as the ecological niche capacity. This is the equilibrium population count given resources, or in other words, given the alpha and the beta. So the birth rate versus death rate versus the rate of perishing in various quadratic encounters. And so this resolves Malthus's problem because this quadratic feedback, negative feedback coefficient stabilizes the dynamics. And as we well know by now, there have been no population count related disasters since 1800 or so. There may be something if we have some uncontrolled proliferating disease that's highly communicable and so on, but all of these are modifications to these exact same models. Now, as an exercise in actually solving these things, let us now go ahead and completely solve this differential equation, and then look at solutions in this regime and that regime to see what is happening there. And actually we will obtain Malthus's solution as the short time limiting case of that when beta becomes very small. Okay, well, all of you have seen such equations before. This is actually a fairly trivial separable ordinary differential equations. You can put all the x to the left-hand side and all the t's to the right-hand side. So this is dx over alpha x minus beta x squared equals dt. So we can simply integrate both sides. Before I do that, however, I need to split up that pesky fraction because we don't know how to integrate this directly, but let's just open that up. So we have 1 over alpha x plus beta x squared. That's the same as 1 over x alpha plus beta x. And this we will say is a over x plus b over alpha plus beta x. So we just split it in the usual way. Let us merge this back and then obtain the equations for a and b. So alpha plus beta x a plus x b is x over alpha plus
is it minus?
Where?
Alpha x.
Oh, it's well spotted. Should be minus. And there as well. So I'll clear up some space just underneath here. So what we have therefore is alpha a minus beta x a plus x b must be equal to 1 for all x. And that means that alpha a is 1 and these terms must consistently be 0. So we have b minus beta a must be 0. And so alpha a is 1, and that's b minus beta a. It has to be 0 because there's no x on the right hand side. And therefore, our a is 1 over alpha, and our b is beta over alpha. So far so good, and now we can proceed to integrate this. Okay, so integral here, that means we have on the left hand side an integral, so a over x, so 1 over alpha over x, 1 over alpha over x, and then b beta over alpha, and that goes here. So beta over alpha, and the denominator is alpha minus beta x. dx equals to, well, integral dt is just t plus a constant. Lovely. Well, we actually know how to integrate 1 overs. These are just logs. Let's make some space and do those logs. One over alpha log x plus beta over alpha 1 over minus beta log alpha minus beta x is t plus a constant. Here it's just a straightforward integration. Beta over alpha gets out in front. We have to divide by 1 over beta when we do the integral. So there it is, and the log of whatever occurs in brackets. So beta here cancels and a minus sign appears. So we have 1 over alpha. Then it's a log. So the log of this minus the log of that. So we have x over alpha minus beta x, and that is our time plus a constant. Okay. Exponentiating both sides. What else shall we do in here? Perhaps move alpha over there. So put an alpha here. Alpha c is just another constant. So take the exponentials. X alpha minus beta x is e to the alpha t plus c. And we will just say, okay, split up the exponential. The exponential of a constant is another constant, so c e alpha t. Good. And the last thing that remains is, this is currently resolved with respect to x. With respect to time, let's actually solve this for x as well. So what we have is x equals c e alpha t alpha minus beta x. Opening up the brackets, collecting the x's. So x is alpha c. Again, I'll put it into a separate constant eventually. E alpha t minus beta c x e alpha t. Move the x's over to the right hand side, divide things out. So we have here x1 plus beta c e alpha t is alpha c e alpha t. And finally, our x as a function of time is alpha c e alpha t, and this is 1 plus beta c e alpha t, where c is an arbitrary constant that depends on the initial tension. This is called a logistic curve, and for that reason this is called a logistic model. So let us make some space and explore the dynamical regimes that we have gleaned at our phase diagram. That's population, and that is time, and this is our ecological niche capacity that we have there, alpha over beta. And that's the population. What would happen if we start our dynamics below this niche capacity? Well, as you've seen from the phase diagram, the population grows. And if we look at this, when t is really small, then this exponential is not particularly large, and what we have is slow growth, right? So if this is small relative to 1, then we basically have growth. Okay, so when we begin at almost the 0 population, what we will get is initially a growth, and then it will stabilize itself and approach the niche capacity. If you look very carefully at this curve, you would notice that this region here, actually can be seen mathematically from analyzing, this is nearly perfectly exponential. So this is the Malthusian. It corresponds to a situation where the population is small and food is still plentiful and there's plenty of space on the planet, which is roughly, 16th, 1700s, when much of the Earth was actually still unpopulated by humans. And then, as the population increases and the resources dwindle, the population approaches some steady state. If we begin in a different place, if we begin there, then the population would still grow and approach the niche. So, something like that. But exactly the same eventual stationary state. However, if we begin at the top where the population exceeds the niche capacity, well, we'll just have a famine on our hands and the population will approach the stationary state from above. And these are the solutions that you can obtain by plugging the corresponding initial conditions into this and just plotting it in MATLAB, Mathematica, or whatever have you. And of course, in this situation, we have one relatively meaningless unstable stationary point at 0 and one meaningful stable stationary point, and no disasters actually happen within this model. Okay, now the summary of what I've told you is you will meet time and again situations when you are given some horribly messy chemical, biological, quantum mechanical, in my case, system and told to make a model. You proceed exactly as these fine gentlemen had proceeded in the course of history. You write some plausible assumptions about it. I mean, degrees of plausibility can vary. You turn those plausible assumptions into mathematical equations and you take appropriate limits to make them into differential equations. As soon as you have a differential equation, not only do you know how to solve it, you are also able to predict, generate the entire range of the dynamical regimes in that system. Which regimes are catastrophic, which regimes are benevolent, how to tip the situation from one into the other. Right? If you'd rather not sit in that particular minimum and maximum, you know that you need to push the population above a certain level to drop yourself into the attractor pool of a different stable stationary point. So this is actually actionable, right, in terms of, for example, social policy, if you have a sophisticated enough model that is close enough to reality. As you can see, even from here, solutions tend to be rather complicated. We have spent good 15 minutes solving the differential equation here, but thankfully it's mostly computers these days, and the sort of models that you will encounter in practical realities will not have one variable in them, but maybe a couple of hundred, and then there's no choice but to use a computer, and this dynamics analysis becomes rather complicated. Some years ago, Russians had lost an intercontinental ballistic missile because they didn't account for a parasitic solution in a differential equation, and when it started, it decided that the shortest path to the United States was through the Earth. And they just crashed into the ground, right? So how these models behave when you incorporate them is up to you to, really get right, but they are really useful. Any questions?